Welcome to my video on estimating limits numerically. A limit tells us what value a function is getting close to as x approaches some number a. When the function is complicated or has a hole at some point, we can estimate the limit by plugging in values of x that get closer and closer to a. So what we want to do here is we want to just look at our typical function. This could be just a random function. So there's x. The y-axis is f of x. Let's just do a nice little curve right here. Now we want to estimate at this point a. But let's say that the function there does something kind of crazy. Maybe it blows up or is undefined. There's a lot of functions that do that. So what we want to do there is take that out, and we're going to put in a circle there because we don't know exactly what's happening. It may go up or down, we don't know. It's undefined in some way. So what we want to do is, in the past we've done this algebraically, but now we want to do it numerically. We want to take values up here, down here, and as we get close, and what we find out is this is called the A minus and then the A plus. So we've got another video on that that talks about the left and right limit. But that's what we're going to do numerically, is evaluate points right around this point of discontinuity or this point in question right here, where A, and then figure out numerically. We've done it algebraically, so that's what we're going to do in this video. So here's our process. It's basically just plug in numbers. So we're going to choose this point we're interested in, A, whatever point that might be. Pick x values approaching A from the left and from the right, and the right would be larger than A and the left would be smaller than A. So compute f of x for those nearby values, and if both sides approach the same number, that's the limit. So if the left and the right hand limits approach the same thing, then that is the number of the limit, and if they don't approach the same number, then they don't exist. So what I want to do now is look at a couple of examples, and the first one is going to be, we want to estimate and I say estimate because we're doing this numerically. X goes to 2, take the limit of the rational function x squared minus 4 over x minus 2. So just like we described in that procedure, what we want to do is we want to calculate x, and then over here we're going to calculate what the value of the function is. So this is going to be x squared minus 4 divided by x minus 2. So the point of interest is 2. So A is going to be 2 in this case. So let's start out at 1.9. We're going from the left. I'm going to calculate this first point for you. So we got 1.9 quantity squared minus 4 divided by 1.9 minus 2. So if we do the math on that, it's minus 0.39 divided by minus 0.1. So that's equal to 3.9. Now let's look at 1.99. I'm just going to do the math for you, and you can do it on your calculator. That's 3.99. Now at 1.999, we're not going to 2, because something strange happens at 2, but we can get arbitrarily close. We can continue doing this. We can continue doing the 9s just as long as we want to. Now this was the A minus case. Now let's look at A plus. In other words, we're coming at it from the upper numbers or from the right. So let's start at 2.001. Putting that in the equation, we're going to get 4.001 and 2.01, 4.01, and 2.1, we're going to get 4.1. So let's plot this on a graph and see if we can make sense of this. We're just going to plot right around this point of interest, and that's going to be 2. So there's going to be 1. There's going to be 3. So 1, 3. And it looks like all of our numbers are right around 4. So we're going to do 4, and let's make this, if there's 4, we'll call this 3. And we got to put a little discontinuity in our graph here. We're putting a little break in our graph there so I can get the scale approximately correct. So there's 5. Now our first point there is 1.9, so that's going to be about right there. And we got 3.9, so that's about right there. And 1.999, we get really close to 4. And then at 1.9999, it's kind of hard to plot on this graph. So we've got some points right there. But now let's just take a look at if we put 1 in there. So if we do, looking at 1 here, so we're going to get 1 minus 4 divided by 1 minus 2. So that's minus 3 divided by minus 1. So that's going to be a 3. So there's our point. We don't know exactly what's happening at. A is equal to 2. Now, let's go from the upper side up here. So at slightly above 2, we get 2.01. And then at 2.01, we get 4.01. And then at 2.1, we get 4.1. Now let's take it evaluated at 3 to kind of complete our line, since all of our points are just right there. At 3, we're going to get 3 squared, let's see, 9 minus 4 divided by 3 minus 2. So that is going to be 5 divided by 1, that's just a 5. So this point is going to be a 5. It looks like we're going to have a line here. And it really goes to about the point 2. Like I said, this graph is not properly drawn, but you can get the idea. The point is, as we come down from the top and from the left, from the lower side, it approaches the same number. It approaches 4. So what we can gather from this is the limit of x goes to 2, x squared minus 4 divided by x minus 2 is equal to 4. So that's our answer. The limit goes to 4, but we do know it does blow up at 2 because that becomes undefined. This ratio becomes undefined because we've got 0 in the bottom. So we don't know exactly what happens. It goes to infinity. Really, the thing goes to infinity right here. But the limit tells us we don't care exactly what the function is at that point. We care what the limit does. That's what we're trying to determine. The limit goes to 4. All right, so there's our first example. Now let's look at a function with a discontinuity. So we're going to make g of x equal to 2x plus 2, and then 2x minus 4, and that's for the region for x less than 1, and this is for x greater than or equal to 1. So at 1, the function changes. Let's just plot that so we can get a better idea of what's going on here. So I'm going to first look at the point to the left of 1. So this is the 2x plus 2. Now x equal to 0, it's just going to be equal to 2. So let's just do 1, 2, 3, 4. 1, 2, 3, 4. And then 1, 2, 3, 4. Minus 4. 1, 2, 3, 4. So there's our x, and this is going to be our g of x right there. So we just determined that at x equal to 0, we get 2. So there's our point at x equal to 0. Now x equal to minus 1, we're going to get that's minus 2 plus 2, so that's going to be 0. And we can tell that this is an equation of a line because it's in the form of mx plus b. So we know it's going to be a line. Now at 2, at 1, this is going to be our point of interest here. So let's draw our line in there, those 2 points, but we really can't go past 1. 2 points determine a line, but it stops at 1, just to the left of 1. Now let's look at the second curve, 2x minus 4. We have to be at greater than or equal to 1. So at 1, 2x minus 4, that's 2, so that's minus 2. So it's going to be down here, this point. Now at x equal to 2, we got 4 minus 4 is 0. Okay, so this is going to be another line. It's just shifted. It's got the same slope, because both have a slope of 2, but they both have an offset. This is the b of 2 and the b of minus 4, if you remember from the equation of a line. So we've got 2 parallel lines going to negative infinity and plus infinity, but there's a discontinuity at 1. So we want to calculate now what we want to do. So let's find numerically the limit as x goes to 1 for g of x. That's a point of discontinuity, a jump, a discontinuity. So once again, we'll do our graph here, our table of numbers. We're going to go just to the left of 1 and to the right of 1. So first of all, let's go to this, just to the left of 1. So that's 0.9. And I'm going to just put the numbers in the equation here. So it's 0.9 times 2 plus 2. That's going to be 3.8. I'm going to do the math for you. You can do it on your calculator. 0.99, 3.98, and 0.999. And we get 3.998. Now we're going to take the case where coming in from the upper or the right side. So we're just above 1. 1.01 minus 1.98. 1.001, and we get minus 1.998. And if we get a little closer to 1, we get 1.001, we get minus 1.9998. Okay, what we can tell basically from this is, since as this number approaches 1 from the left, this number approaches 1 from the right, big difference. So what that implies to us is, from what we know about limits is, so the limit does not exist at a equal to 1, or as x goes to 1.